Tonight's video is part 2 of section 3.3 on the first derivative test. Your homework from this section will be 61 through 73, 85 through 89. We'll be working on those problems in class tomorrow and Friday, and they will be due next Tuesday. Today is going to be about analyzing graphs. So most of this you know. I'm just going to kind of sum it up again with a couple of different graphs. So I drew a sketch of a graph, and here are some things I want you to denote. First off, please realize this is the graph of f prime, my first derivative. I am recording the slope of the tangent line of the graph of f on this graph. F prime of x, those y outputs that are greater than 0. So again, here's f prime here. All of these values here, their y values are greater than 0. That's a y. So what x values will the y be greater than 0? Well, that's from -2 to positive infinity. All of these x values will produce y values on my first derivative graph that are positive. For what x values on my first derivative graph will the y be less than 0 or negative? Well, here all of these points, their y values are all negative on my first derivative. And what x's does that happen at? From negative infinity to -2. And f prime of -2 happens to equal 0. My y is 0. When my x is -2, my y is 0. Well, if my first derivative is 0, that means that x equals -2 is a critical number. Right? Isn't that what that means? Isn't that how I find a critical number? I set the first derivative equal to 0. We find out what x values. Well, here it is graphically. It's -2. So let's take it a step further. I'm going to take that graph and let's make a sign chart for it like we did in pre-calc. Let me scoot that up just a little bit more. So here is my first derivative sign chart. This is like the x-axis. What I'm going to do is I'm going to put the critical number on here, -2, and that's for this graph up here. So it's like a condensed version of this. So -2, and then on this side, all of those y values are negative. On this side, all of those y values are positive. Let's take it a step further. Let's talk about f. If on the first derivative, these y values are negative, my outputs are negative for these x values, that means that I have a negative slope. I have a negative slope, like so. If I have a negative slope, isn't that function f decreasing? It's a decreasing function. For these x values on f prime, my y output is positive, so that means that the slope is positive, right? It's a positive output, positive slope at these x values on my original graph f. And so if I have a positive slope, isn't that f an increasing function? It's increasing, it's positive. Please note something. On a first derivative, I'm going to use negative and positive, and the one before it, which would be f, right before the first derivative would be f, I transfer those words from negative to decreasing, from positive to increasing. It will always be like this. So let me take it a step further, the first derivative test. Since f prime is changing from negative to positive at x equals -2, then f, my original function, has a relative min at -2 and whatever that y output is of f of -2. Let's take a look at another graph. Let's do the same thing. I'm going to analyze this graph. So here's a parabolic shape. It's going to go through -2 and 2. So please denote, first off, you need to look, what is this a graph of? This is a graph of f prime. This is not my original graph. So this is all recording the slope of the tangent line of f at these x values. So f prime of x, when that y output for some x values is greater than 0, let's see where that is, right here. Isn't all these y outputs going to be greater than 0? And over here, which x values is that? Well, from -infinity to -2, and from 2 to infinity. Well, what x values will my y output on my first derivative be negative or less than 0? Well, that's in between. From -2 to 2, all of these y outputs are negative. The first derivative is negative for these x values. Well, f prime of -2 is equal to 0, because my y is 0. And for f prime of 2, my first derivative, is equal to 0. It's my y output. So isn't that how we find critical numbers? One way to find critical numbers is we take the first derivative, we find out what x values is equal to 0. Well, we found them out. It's -2 and 2. So these are both critical numbers. In other words, critical numbers are, these are the x values, and I can get the point. These are potential points where on my original f function, I could have a relative min or max at -2 and at 2. Not on this graph, on f. So let's do the sign chart again. The sign chart for f prime. Record the critical numbers -2 and 2. And so over here, those y outputs that we recorded as positive, negative, positive. I'm going to go ahead and also write down what's happening on f. If f prime, or my first derivative, is positive values, then f is an increasing function here, everywhere, up to here. Then it decreases, then it increases. Since f prime is changing from positive to negative at x equals -2, then f has a relative maximum at -2 f of -2. I just don't have the function, I don't know what it is, what that y output is. And one more. Since f prime is changing from negative to positive at x equals 2, then f, my original function, has a relative min at that ordered pair 2, f of 2. I'm going to switch gears, talk about our bug. Our bug didn't go anywhere. It's going to come up here again, and this is going to feel like all the same stuff, which is okay. Motion along a line. Well, given a position function, s of t, I can find that with the velocity function. How? By taking the first derivative. If I want to find I can find an interval when the particle, or my bug, is moving to the right, using my velocity function. I can find an interval when the particle is moving to the left, and I can find the time when the particle changes direction. So I'm going to take some given position function. I'm going to go ahead and find the velocity function by taking the first derivative, so that is the first derivative. I can find when the particle is moving to the right. So the right means when the y outputs are positive. We know that graphically. We've done a graph of this bug. And so now these y outputs on the first derivative, they're positive. So let's go ahead and find those, but without a graph this time. Let's find it algebraically. So I'm going to take my velocity function, and so this is my function, and I want the outputs to be greater than 0. I want for what t's is this going to be greater than 0? Again, what t's, what times will this output be greater than 0? In other words, positive. because at those times, that's when my bug is going to the right. So I'm going to subtract 8. I'm going to divide by -2, and please remember on a inequality, that means I have to change the sign when I multiply or divide both sides by a negative number. So that means when my time is less than 4, probably 4 seconds, my bug is moving to the right from 0 to 4. I can't include 0 because he has stopped. Part C. Velocity. I'm going to look at the velocity function again. It's left. Left means when these y outputs, like what x, or in other words, really what t's, what times, will the y outputs be negative or less than 0. So I'm going to take that same velocity function. What times will this output be negative? In other words, less than 0. Again, I'm going to subtract 8. I'm going to divide both sides by a -2. I'm going to flip the sign around, so it means when my time is greater than 4. So from 4 to infinity. At x equals 4, the particle changes direction from right to left. It changes direction from right to left. That's it. I will see you tomorrow.